Okay, so we got to the last talk of this session. It is going to be very different from the previous in the way and the content. I personally was following this project since it was more or less started.
Yeah.
So let me introduce Qureshi from NVIDIA, and this is going to talk about the work to access storage from GPUs, led by Wen-mei from UIC and NVIDIA.
Yep. Thank you, Professor, for your introduction. Hi, I'm Zaid, and I'll be talking about our work on GPU-initiated on-demand high-throughput storage access in the BaM system architecture. This work was done at the University of Illinois in collaboration with NVIDIA, IBM Research, University at Buffalo, and Stanford University. Due to their impressive performance, accelerators are becoming a prominent part of many application pipelines. However, accelerator memory capacity is not keeping up with the memory demands of these applications. For example, since 2016, in the span of 5 years, recommendation system memory demands increased by 10,000 times, while accelerator memory capacity increased by less than 7 times. We term this the accelerator memory capacity wall. The traditional solution to address the limited GPU memory capacity is to use CPU application software to partition the data and orchestrate data movement. For example, the CPU can move a tile of data from storage to CPU memory, and then move a subtile to the GPU memory, and then launch a GPU compute kernel that operates on that subtile. Although this approach has worked well for traditional GPU applications, it has a few shortcomings for emerging applications. For example, if the GPU threads ever need to make sparse access to the data, this approach leads to high I/O amplification. Furthermore, if GPU threads ever need to address more data than can fit in GPU memory, this approach does not work. Alternatively, systems like GPUFS, as pioneered by Professor Silberstein, allow GPU threads to make on-demand requests to software on the CPU, which fetch and move data on their behalf. However, when multiple threads make such requests in parallel, the CPU software overheads and costly synchronization easily limit the system's performance. Lastly, the user can provision enough CPU DRAM in the system, pin the data from storage into the CPU DRAM, and then allow the GPU threads to access the data directly from CPU DRAM. Although this approach has been shown to be quite performant, scaling CPU DRAM with dataset size is an extremely expensive proposition in the foreseeable future. Furthermore, applications must wait for the entire dataset to be present in CPU memory before it can launch any compute kernels on the GPU. Our solution to break the accelerator memory capacity wall is BaM, where we expand the effective GPU memory with storage. To this end, we move the storage I/O queues to the GPU memory to allow GPU threads to make I/O requests for data on storage directly. We design a highly concurrent software-managed cache to use the fast GPU memory for data reuse and to optimize storage bandwidth utilization. And we provide an array-like abstraction that is familiar to GPU programmers, making it easy for them to integrate BaM into their applications. With BaM, GPU threads can access data where it is, be it memory or storage. Now let me show you how a GPU thread uses BaM to access very large data efficiently. As I just mentioned, GPU threads use an array-like abstraction to access data backed by BaM, and GPU threads, each of them can calculate the offset for the data that they need and use our software coalescer to pick a leader and to reduce contention in the cache state management. The leader can probe the cache, and if the access is a hit, the threads can access the data directly from the cache. And if it's a miss, the leader needs to allocate space in the cache, prepare an I/O command, and then submit that I/O command in the submission queue for the storage controller that's in GPU memory. Here, we develop a novel technique to allow many GPU threads to enqueue their requests in parallel and to coalesce doorbell writes efficiently. Once the doorbell is rung, the controller can read these requests, process them, and eventually will post completion queue entries in the completion queue in the GPU memory. The GPU threads poll for these completion queue entries, and when they find the appropriate one, they can clean up the completion and submission queues to make space for future requests and update the cache line state so that other threads can access the same cache line and access the data from the GPU cache. Now that GPU threads can access data in storage directly, naturally the question is, can BaM tolerate the relatively high storage access latency? The needed queue depth to hide latency at a specific throughput can be modeled using Little's law. The GPU provides a PCIe Gen 4 x16 interface, which has 32 gigabytes per second of unidirectional bandwidth, of which 25 gigabytes per second are usable for data transfers. If we want to move data in 512-byte granularities, we need to maintain a throughput of 50 million I/O operations per second. Using the Intel Optane P5800X SSD as an example, it has a total access latency of 10 microseconds. Thus, using Little's law, we know that we need to maintain a minimum queue depth of at least 500 requests to be able to saturate the GPU's interface. However, we need many more requests in the system because we need to maintain this queue depth over time to sustain the desired bandwidth. To see if BaM can provide such high I/O level parallelism, we prototype BaM using real hardware by attaching a PCI expansion chassis to the host system whose specifications are shown on the slides. The PCI expansion chassis features high-end PCI switches, which enable us to scale the number of PCI devices in the system and provide high-throughput peer-to-peer access between the devices. We populate the PCI expansion chassis with an NVIDIA 100 GPU and up to 10 Intel Optane SSDs. We measure BaM's achievable I/O throughput as we scale the number of SSDs. Here we'll launch a GPU kernel where each GPU thread makes one I/O request to an SSD. For 4 kilobyte accesses, BaM easily saturates the 1.5 million IOPS of a single SSD and continues to scale up to 4 SSDs, where BaM very nearly saturates the GPU's PCI interface. For 5 12-byte accesses, BaM scales up to 45 million IOPS, again, very nearly saturating the GPU's PCI interface. But is saturating the GPU's PCI interface sufficient? Recall that all the state-of-the-arts for processing very large data, be it proactive tiling, UVM or GPUFS, or using abundant CPU memory, all require getting the data into the GPU through its PCI interface. As such, efficiently utilizing this interface is key to performance. To see if BaM can overcome latency and provide such high performance for real applications, we evaluate BaM with 2 graph analytic workloads, BFS and connected components. We execute these workloads on 5 of the largest graphs from the sweet sparse matrix collection. For the target baseline, we use the state-of-the-art GPU accelerated graph traversal library, which pins the data from storage into the CPU memory and allows the GPU threads to access the data directly. We time both the initial file read time as well as the app execution for the target baseline. We know that this is a very optimistic baseline as it assumes that there's abundant CPU memory for the entire data set. Here we plot the execution time for both BaM and the target system with 4 SSDs. BaM is either on par with or outperforms this more expensive system for 2 reasons. One, because BaM allows GPU threads to access data on demand, it completely eliminates the initial file read overhead. Second, these applications expose large amounts of data parallelism, allowing BaM to keep many I/O requests in flight and almost always saturate the GPU's PCI interface. Next, we evaluate BaM with the data analytics workload. We use the New York City taxi ride dataset, which has data for over 1.7 billion taxi rides since 2009. For the baseline, we use the state-of-the-art GPU accelerated data analytics framework by NVIDIA called Rapids. It uses the proactive tiling approach to process datasets that are larger than GPU memory. However, to get an even more optimistic baseline, prior to execution of any query with Rapids, we pin the entire dataset in the Linux page cache. Thus, during execution of Rapids, Rapids makes no storage I/O requests in the evaluation we're about to show. For the query, we'll look at trying to get the average dollar per mile the driver makes for taxi rides that are at least 30 miles. We can build this query by starting with a simple one that just scans the trip distance column. Then we can add each needed data-dependent column one by one until we get the penultimate query in query 6. Here we show both BaM and Rapids throughput in executing these queries as well as the I/O amplification suffered. BaM significantly outperforms Rapids for 2 reasons. One, because it allows GPU threads to make on-demand requests, it has significantly less I/O amplification. And second, it uses the GPU's massive parallelism to manage both the I/O and the memory. In conclusion, to break the accelerator memory capacity wall, we propose BaM, where GPU threads can access data where it is, be it memory or storage. Our prototype shows that BaM not only increases the GPU's effective memory capacity, but reduces I/O amplification, improves performance, and is significantly less expensive than DRAM-based solutions. BaM has opened up new interesting research opportunities and questions in the accelerator memory storage hierarchy. We welcome any collaboration on any of these topics. We envision a future in which accelerator programmers write code that operates on data, and systems like BaM find and fetch the data efficiently. We thank all of our collaborators and supporters, without whom this work would not have been done in any timely manner. We invite you to our poster session tomorrow, and you might have the opportunity to get some treats if you can guess what BaM stands for, and we thank you for your time.